Thank you very much. And thanks very much to the organizers for giving me the opportunity to be here and to present these results. So I will talk about joint work with Federico Ambrosino at DESY and Jared Watts at King's College London. Roughly, I would like to first maybe remind you a little bit about topological defects in 2D CFTs and an application they have in renormalization group flows. Then we will see that maybe we can improve the situation we see there by including a more general class of defects, which are these translation variant defects. I want to talk a little bit about these. And at the very end, if there is time, we will maybe see a relation to integrability. Okay, so that's the plan. And okay, so here is a rough map of defects. So we have already heard several talks when it talks about defects, which can be localized on submanifolds of some dimension. And then if your quantum field theory is conformal, well, then there's a special class of defects, which are these conformal defects. And within there, you can find an even more special class, which are the topological defects, which you can freely deform on the world volume of your quantum field theory. I would like to talk about so these translation variant defects I mentioned, they sit a little bit on the side of this picture. So, these, I will define what these are, but they are not conformal, or if they are conformal, then they are actually also automatically topological, at least in this case of two-dimensional quantum field theory, which I will talk about. So we will look at these during the talk. Good. So let me remind you a little bit how you can describe topological symmetries in two-dimensional quantum field theory and in conformal field theory. So I have drawn 3 pictures, and I will use all of these. So this is the sort of worldsheet perspective, if you want. So that's a two-dimensional surface on which your two-dimensional quantum field theory is defined, and you can have point observables and maybe these line defects, and if they're topological, you can move these around without affecting the value of correlation functions. Now, this situation you can describe from this SymTFT perspective, where you have a 3-dimensional topological field theory, which has a non-topological boundary and a topological boundary, and then this topological line defect would be a line defect on the topological boundary, making it automatically topological for the entire theory. Now, this picture here applies fairly generally in two-dimensional quantum field theories, where you make a selection of your topological symmetry. So that could be some spherical fusion category, and that allows you then to glue it to this 3-dimensional theory. Now, in the special situation that you are not in 2D quantum field theory, but in two-dimensional conformal field theory, and if you have chosen your topological symmetry to be large enough, then you can unfold this picture if you want. You can take a square root, and then you arrive at this picture, which I will refer to as chiral topological field theory. And now we have 2 non-topological boundaries, one on which the holomorphic degrees of freedom of the field theory live, and one on which the anti-holomorphic degrees of freedom live. Right, and then this topological boundary here gets replaced by a topological surface defect, which separates the holomorphic and anti-holomorphic boundary, and you can go from this picture back to the symmetry TFT picture by folding it at this surface defect, which sits in the middle. So I want to do an example to say what I mean by this large enough F. So let's look at the two-dimensional Ising model. So that's our favorite conformal field theory in 2 dimensions. It has central charge 1/2. It has 3 primary fields. I've given their holomorphic and anti-holomorphic scaling dimension here. It also has 3 elementary topological defects: the identity, the spin flip 1, which generates the Z2 symmetry, and the duality defect, which has these composition rules. And so if you look at these, you notice that you can make 3 choices for a fusion subcategory, so 3 choices of topological symmetry in this model. You could just pick the identity. That's certainly closed under fusion, and then the fields, the local fields which would live on the non-topological boundary without generating a Wilson line, well, that's just every field in the theory. If I take this subcategory, then the local fields are 1 and epsilon, right? So again, so there's some non-factorized degree of freedom there because, well, it has both components. But if I take the full symmetry I have at my disposal, so all 3 of them, then the remaining fields which can live on the non-topological boundary without having a line defect attached to it, which reaches in the interior, well, that's just as a primary the identity. And so therefore, all of the fields which can live here are the holomorphic tensor, the anti-holomorphic field. So I've written this as V. V stands for VOA, tensored with the anti-holomorphic copy of it. Right? And so when I say large enough symmetry, I mean I have to pick something which is large enough so that the degrees of freedom factorize. And if that is the case, then I can unfold this picture. And so I get this nice separation also in the geometry of the topological field theory into the holomorphic and anti-holomorphic degrees of freedom. And so that's not a special thing that happens in the Ising model. That's something you can do in every rational conformal field theory. It's always possible to choose this symmetry large enough for that to happen. So I later make use a lot of this chiral TFT picture because it makes it clear which fields are holomorphic and which fields are anti-holomorphic, and so that's useful to know. Okay. Then I said I want to look at applications of topological symmetries to renormalization group flows as one motivation why I then want to talk about these more general defects. So let's remind us what we are doing. So we have some conformal field theory in the UV, and we want to push it off the critical point with some relevant perturbation, and if we are lucky, it'll then flow to some other conformal field theory in the infrared. That could be gapped, right? So that could just be a topological field theory, but it could also be a gapless theory, then it's the non-trivial conformal field theory. And so sort of the typical situation is that for the conformal field theory, you have a fairly large topological symmetry, right, whatever that may mean. But then if you push it off the critical point, there then again be typically only few topological symmetries which survive along the flow, so which would then exist along all of this flow. And so if you want a symmetry TFT which is valid along the whole RG flow, well, then you have to work with a smaller topological symmetry which is preserved, but then you have a situation where you have a fixed 3D TFT, so that's independent, oh, that should have been a mu here, sorry. So that's independent of the perturbing strengths, and the topological boundary also independent, but the non-topological boundary flows. Right. So how do I know what this smaller topological symmetry is? Well, that's something you can detect at the point of the UV CFT. So in SymTFT, the picture is this. So you're asking which topological defects, so which of these red lines, commute with the perturbing field. Right? So in SymTFT, that's the picture. So think of this as a local picture. So we wanted, if we take the topological defect past one side of the field, to be the same as taking it past on the other side of the field. So if that happens, then this topological defect remains topological along the entire flow, and so that's the topological symmetry which we have at our disposal for this whole family of theories. Okay, so let's again look at our Ising example to see what that looks like there. So okay, that's from the previous slide, what the field content and the topological defects were. So we have two relevant perturbations, sigma and epsilon. Epsilon generates the temperature perturbation, so that pushes the conformal field theory of the critical point, and it flows to some massive theory. I mean, I'm writing plus mu, but I'm not thinking of mu as having a specific sign, so it's sort of really the space of flows generated by this parameter mu. But in any case, you get a massive theory. And sigma is the perturbation which amounts to applying an external magnetic field. And that also pushes your theory out of criticality and flows it into some massive theory. You could do some You could do some combination of these, but then the more relevant one would win. So you can now compute what is the topological symmetry which is preserved by each of these. Now, if you do the temperature perturbation, so the perturbation by epsilon, this relation from the previous slide, let me go back. So this relation here is satisfied by two of the topological defects, the identity and the spin flip one, whereas for the magnetic field perturbation, only the identity survives, so there's really no topological symmetry which is preserved for that perturbation. Okay. So that picture may motivate one to ask, well, is there some larger thing I can do which maybe has more things which are preserved along these flows? So that's maybe one motivation for this project. And so the larger thing will be these translation invariant defects. So let me say what these are. So I want to look at defects which, if I put them on a cylinder, I can move them rigidly up and down, but I can't maybe deform them arbitrarily, right? So if I do go from here to here, that may change the correlator, but if I move it rigidly up and down, that does not change a correlator. So in terms of sort of the Hamiltonian, that means that the operator associated to this defect commutes with the Hamiltonian of the theory. Right, so that's a, yes, we need some microphone. And
are these related to holomorphic defects if you do like radial quantization, or is a different set of stuff?
Say that again. Holomorphic defects.
Holomorphic, yeah, just that they commute like with L0 bar, the anti-chiral Virasoro algebra. You know,
right. So we will have an example which looks like that later. So these give examples, I would say. Right. More questions. Okay, so we can't do this, but we can move them up and down. So that's what you get if you can commute with the Hamiltonian. It's a weaker condition than being topological. Right. Now, these share some good properties with topological defects, even though we can, so we have less freedom in deforming them. Sort of the mathematical structure which we find is not so different. And the reason for this is that we can still have a well-defined fusion operation. So in the sort of more general defects, which appeared also in Yifan's talk, if you try to move two defects close to each other, you will encounter some singularity. So it's not so clear what you mean by the fusion operation. Some work has to be done, so then you get this notion of OPE of defects, which may be associative or not. But here these problems are not present because there is no singularity, because you do have this translation variance. You can just push this onto this one, and then you have a new translation variant defect. So you do have this fusion operation, and you also have a notion of topological junctions. So you can ask, if I have two of these, say, or any number, can I find a topological junction from this into any other number of these topological defects? And you can think of these then as morphisms for your category of topological defects. So you do get a monoidal category.
The defect translation invariant only in one direction or in all directions?
Well, I posit that if you translate it in that direction, you won't notice.
Sorry, say it again?
So if you translate it in the other direction, you won't.
Yeah, okay, I understand, but I could put the defect in the other way around, no?
So if you rotate it,
yes,
then that'll typically not be invariant. So in the defects I present later, if you would rotate them, you also would have to modify some coupling constant. So it's not invariant under rotation, for example.
So how is this compatible with the relativistic invariance of the theory?
Okay. Well, does it have to be? I mean, sorry, what?
Yeah, the defect itself could break some conformal.
So the defect is not conformally invariant? So it does. So is that an answer or another problem?
A statement.
It's a statement. Okay, I agree. Okay, so these are not conformal, and they're just objects which exist in your theory, and the whole theory is like a two-dimensional conformal field theory, so that would make it relativistic, I guess. But these will break some of the symmetry.
Does the topological invariance of the junction, that seems like it doesn't necessarily follow from the translation invariance.
No, that's an extra condition. So there can be fields which live on these defects which are not translation invariant, and ones which are, and the ones which are, I want to say these are my morphisms. Right, and then if I do this, I get a monoidal category of translation invariant defects. Oh, there's good. Now let's see. No, please. Righto. So the point I want to make is that we do have topological defects, and they form a monoidal category. And in fact, there are a full subcategory, a full monoidal subcategory of these translation invariant defects. So the these translation invariant defects are like an extension of your topological symmetry, if you want. They don't really deserve to be called a topological symmetry because you can't deform them arbitrarily. But as a monoidal category, these properly sit in, well, they typically properly sit in here, but they're also fully embedded, so that all morphisms, well, I don't never mind. So they're fully embedded as a monoidal category. So the tensor product also compatible in particular, right? So tensoring here is compatible with tensoring here. Okay.
Because you have a junction between two topological defects, you can make the junction very non-topological.
Yeah, right. So, okay, that's, in my category of topological defects, I only look at topological junctions as morphisms. So,
okay.
So trivially, yeah, it's a full.
But in the larger category,
I also only take topological junctions.
Okay.
Okay. So, let's try and find an example. So that comes back to, I think, what you said. So in 2D CFT, so we don't perturb the conformal field theory yet. That comes later. But inside conformal field theory, we want to construct examples of these translation invariant defects. So here's a mechanism to do this. So you pick a topological defect, and you see, does this topological defect support a chiral, like a purely holomorphic defect field? Right, so in my unfolded chiral TFT picture, that would look like this. So I have a field which doesn't connect to the antiholomorphic boundary, it only connects to the holomorphic boundary, and so therefore it's a holomorphic field. But it's also localized on the defect, because this junction may only exist where it intersects with the defect. And so then so that's again the same construction we saw in Yifan's talk, which is I take the defect and I perturb it by this field which lives on the defect. So I insert this line integral here, integral along the defect, exponentiated on the defect, and so that's my perturbed object. Okay, I could, and so then if I do this, I claim this automatically commutes with the Hamiltonian of the conformal field theory. And the stupid reason why it will do this is that if you look at this picture, so I'm asking, can I translate this whole defect in the t direction? But if I have a holomorphic field, the derivative in the t direction, I can trade it for a derivative in the s direction here. And so then it becomes something which is like shifting the integration parameter, and I can absorb that into the integral. So sort of fairly trivially, these commute with the conformal Hamiltonian. They actually also commute with all the anti-holomorphic Virasoro generators in this example. But in particular, they commute with the conformal Hamiltonian. So that's an example of a translation invariant defect, and it's in general not topological. You can do the same for an anti-holomorphic field. So then that's one which connects to the anti-holomorphic boundary and ends on this line. And then the same argument goes, and you again have examples. Okay. So if you see these two examples, you may ask, well, can I do both of them simultaneously? Can I have like a holomorphic and an anti-holomorphic perturbation at the same time? And the answer is yes, provided that the two fields commute on the defect. So if your holomorphic and anti-holomorphic defect fields commute, then you can do this joint perturbation with independent perturbing strengths, and that's still translationally invariant. And so this condition that they commute, if I write that in my chiral TFT picture, it means that these two diagrams are equal. Okay. So does that ever happen? Yeah, that happens a lot, because if you fuse a chirally and an anti-chirally perturbed defect, well, then you will get one which is of this form here. And because in this situation, these two junctions don't see each other, they, after fusion, will still satisfy this commutation property. Right, so there we have a fairly large class of these translation invariant defects. Now, in the topological defects, it's useful to look at the sort of categorical structure they produce. And so I want to do the same thing now for these translation invariant defects, which you obtain by this perturbation method. And so here's one way to phrase this mathematically. So that becomes a problem in representation theory. And in presenting this, I will make the simplifying assumption that my surface defect is the identity. So if I go back a slide, that this surface defect here, which selects which conformal field theory I'm working in, that is the trivial surface defect, and then it means I'm looking at the diagonal field theory. So in this case, my fusion category of lines on the surface of topological, so my topological symmetry is just given by the braided category of lines in the chiral conformal field theory. Then let X be the representation in which my perturbing field lives. Then given this object, I can define a new object, which is the tensor algebra of X. So that's like a tensor algebra of a vector space, but now you do it internal to this category here. You have to complete it, but let's skim over that. And so the tensor algebra looks like this. And then it turns out, luckily we also had to talk about Hopf algebras already. T of X is a Hopf algebra, but it's now not a Hopf algebra in vector spaces, but it's a Hopf algebra in this braided category. But it is a Hopf algebra, so it's an algebra and it has a coproduct, and so its modules, so you can talk about the category of its modules, and this category is automatically monoidal. So I can talk about the category of T of X modules in C, in this braided category, and I claim that sort of the chirally perturbed defects, where I perturb by just a holomorphic defect fields, that's monoidally equivalent to this category of modules over this Hopf algebra. So if you want to have a representation theoretic perspective, that would be it. And if you want to do these joint perturbations of a holomorphic and an anti-holomorphic field, where we had the condition that they should commute, well, that you can also phrase in representation theory, then you have a bimodule for this Hopf algebra. And so this commutation here relates to a property of a bimodule that the left and the right action have to commute. Okay, so now we have this category of translation invariant defects which we get out of perturbation. It does, however, have some properties which are maybe less familiar if one is used to working with these fusion categories for topological symmetries. So it's still abelian, so it still has kernels and co-kernels, but it's typically quite far from being semi-simple. It does have simple objects, and it typically has continuous families of simple objects, so it's quite large. And it has the funny property that if you take the tensor product of two simples, the output is generically again simple. So that's surprising if you are more used to semi-simple categories, but that's nonetheless true. It is also rigid, so you have duals, but it has then the funny property that the left and the right duals are typically not the same, so you can't do loops even though you have duals.
Can you define F symbols for translation invariant defects that are not topological defects?
And so you see, once you say F symbol, you are sort of thinking that you have that everything is a direct sum of simples. That's not the case here. This category is not semi-simple. So you cannot describe it by just writing F symbol.
Maybe a different question is, can you define an associator?
Oh yeah.
Okay.
So the associator, right? So the associator comes out of the associator from C, essentially, because and from the coproduct. But the coproduct is sort of strictly associative.
So you still have pentagon equations and everything?
Sorry, what?
You still have pentagon equations?
Well, it's an associator, and it's an honest monoidal category, so the associator satisfies the pentagon equation, and it sort of basically comes from the one in C.
I was confused that it seems to me that to define associator and pentagon equation, you need to be able to band the defects on top of only translating
Well,
them.
no, because you can also do that on the line by trying to push these junctions past each other, right? So
Okay.
In any CFT, even irrational CFT, I guess one can define its KDV charges out of the Virasoro generators. They are also translationally invariant defects.
But they're not, indeed. So you're saying these are more examples. That's almost right, once we agree on the language. So how should I say? You can, for example, take the stress tensor or higher sort of combinations of the stress tensor and integrate it along a line. But in my language, that's not a defect because it's not compatible with factorization.
So it doesn't give you a nice Hilbert space.
Right.
I see. Okay, thank you.
But, sort of, I referenced that earlier. In the work of Bajanov, Lukyanov, and Zamolodchikov, of course, they started with these perturbed defects, and then they said in the expansion, as you make your perturbation parameter large, it can be expanded in terms of these local charges. Okay. So, boundary flows, I will skip the boundary flows, and I want to now perturb the two-dimensional conformal field theory as well. So here's my little picture. So I have a conformal field theory in the UV, I push it off the critical point, and I want it to flow to some infrared theory. Then we do have topological defects in the UV theory and these translation invariant defects in the UV theory. And maybe some topological defects survive as we perturb the theory, so commute with the perturbing field. But maybe also some of the translation invariant defects survive. And so maybe there's sort of more now which can persist when we are gone out of the critical point here. And now there's a fun observation, which is that if you have a defect which is both translation invariant and conformal, then it is topological. And so therefore, even though these are not topological and not conformal at the endpoint of the flow, they will be both, and so all of this will still flow to topological defects in the infrared theory. So in a way, if you can find this, there's a hope that it gives you access to more topological symmetry in the infrared theory. Right. So how do we, again, let me remind you, how do we detect these? That was this condition here, now written in chiral field theory. So these ones, these topological ones, which are topological in the perturbed theory, are where I can take the perturbation, where the defects commute with the perturbing field in that way. Now, what about these? So then back to this one. So this one here, that's a condition which is phrased at the UV point. So here I decide which of my defects which are present here survive along the perturbation. And now I want to do the same with these defects here. So there's a simple condition which selects part of these translation invariant defects and which guarantees for you that they persist along the flow. So let me call this the bulk commutation condition. And it's a funny combination of the two pictures we had, this picture and, sorry, let me go back a bit, and this picture here. So, okay, so what does it look like? Well, here it is. So if the commutator of the bulk field with the defect is equal to the commutator of the two boundary fields, the chiral and the antichiral one, then the perturbed defect commutes with the perturbed Hamiltonian. And so that's the statement order by order in perturbation theory. And notice that you always get for free a one-parameter family of solutions. So you find one solution to this, but it translates into a one-parameter family of these defects because you still have a free parameter which gives the relative strength of the holomorphic and anti-holomorphic perturbing strengths. Okay, so whenever we can solve this condition, we have this one-parameter family of translation invariant defect which persists along the flow. So let's look at this in the easing CFT, which was our example. So we had these two directions, the magnetic and the temperature perturbation. In the magnetic direction, there's at least one more defect you can have. And the way you construct this is you take the identity and the duality defect at the critical point and you perturb it by these two fields, and that solves the commutation condition. And so this defect persists along this line of this magnetically perturbed easing model, right? So this means indeed there's more symmetry, if you want, preserved if you take into account this larger class of defects. So for the temperature perturbation also, and then there's even more, right? Because that doesn't get closed under fusion, so you'd sort of have to look at what are all the fusion products and so on. But okay, so this one certainly is there. For the temperature perturbation, you can take the duality defect and you can perturb it by this field, and that also solves the bulk commutation relation. So then, in addition to the identity in S, you do have this translation variant, but not topological defect, which is preserved along this flow. And so if you've done integrability and conformal field theory, then you will not be surprised by that statement, because you know that these two directions are integrable as deformations of the easing theory. Oh, yes. And so in general, one expects these perturbations of minimal models to be integrable. And yeah. So there's also a relation to representation theory now. Maybe that one I can still say because it's pretty. So remember we had C, the Wilson lines of the chiral TFT. Now the bulk field which perturbs our theory defines a morphism in here from X and X dual into the tensor unit. And that one can check becomes a Hopf pairing on these two Hopf algebras. And we also had Hopf pairings already. That was this Fourier transformation in the earlier talk. There was well, that's an instance of a Hopf pairing. Okay, and so this data you can now use to define something called the Jetter-Drinfeld module. So these perturbations which are compatible with the bulk deformation of the CFT, this commutation condition which I had, that actually is the same as talking about Jetter-Drinfeld modules, and never mind what these are, the important information is that they do have a name, and so there is something to be said about them. Okay, well, that's how they are defined, but I feel I should maybe not go through that. And so I want to maybe show this table. So how generic are these solutions to this commutation relation for perturbations, at least in minimal models? So for the integrable perturbations, you can always solve this condition. You can even check that the various defects in this one parameter family mutually commute. So you've got an infinite set of mutually commuting non-local charges, hence the title of the talk. You also actually have also local charges, which are like the higher KdV charges, which you just mentioned. But then there are more solutions. So there are some sporadic solutions for other perturbations, which do all require regularization. So there's a little star if they actually work, if one properly regularizes them. But there are more solutions, and in not all of these models you do find these higher conserved charges. So that's interesting because they may indicate that there's sort of like another mechanism to maybe see integrability. Okay, functional relations I will skip and I will summarize. We have this larger class of defects, and these can be detected at the UV CFT, and that's an interesting class to consider. Thank you very much.
How important is unitarity in your discussion? I think not.
Not, I think, is the answer to that.
And if not, then in the case of the icing, I mean, with the sigma deformation with the imaginary, coupling, then there's a flow to the Li-Yang CFT. Right. And so, how does the Fibonacci lines in the Li-Yang originates from your translation invariant lines?
Right, so now we're at the point where it would have been good if I had already had the time to investigate the easing model in detail in that language. But I don't know. So maybe I can flash this briefly. You do have this extra complex parameter here, right? And so you should really think of the perturbation strength as a complex parameter. And so as you walk through the complex plane, there will be sort of some Stokes effects where the asymptotic behavior changes. And I would expect that that happens when you transition from one infrared behavior to some other infrared behavior, but that's on the to-do list.
I see. Is it easy to see some more specific observable, like quantum dimension, how it changes along the flow?
So the quantum dimension, I would say I am losing as an observable because I can't form a loop anymore. Because to have a loop, I need something trivial into the product and out of the product, and I typically only have one of the two.
Right. The same will go for the associator, I suppose. Because you want to extract numbers from the associator, then you have to do that.
So for the associator, I would even have problems to say how I would define this. But yeah, so you could try to take two simple ones and put them into another simple. But typically that doesn't work because the tensor product of two simples is again itself simple, so it wouldn't have these submodules anymore.
Thank you.
So for the Ising example, am I right that if you turn on both deformations, there's no non-topological defect that survives?
Right. So that so I would also expect that. We didn't look at this, but I think it is at least there's a good evidence that the joint perturbation is not integrable, and so that one wouldn't really expect that it's anything interesting which you can say. So I would also expect that if I would switch on both of them simultaneously, then maybe I can't solve this condition. But we didn't try.
Okay. And relatedly, so it's just an expectation. Is there something more to say between the relation of the existence of these defects and integrability, or?
Right. So okay, that's a little bit this list. So what would integrability mean for you, right? So oftentimes it means that you say I've got an infinite number of charges in involution, or you could have maybe you want to say I have an integrable scattering theory where all scattering processes can be decomposed into two particle scatterings, and so this latter point of view is related to the existence of higher conserved charges in the perturbed theory, and so one can ask, in these models we looked at, does the perturbed theory have such higher conserved charges? And so in these cases, which are known to be integrable perturbations, the answer is yes. We find some solutions where the answer is no, so that's an interesting thing to look at. But also these perturbations require regularization, so we have to check if that's an issue or if they can be regularized, and if that's interesting then. So that's on the to-do list.
Thank you.
Thanks for a nice talk. So I remember that if you start with Ising, if you're deformed by the sigma fields along the flow, there is some relation between the excitations and the E8 group, right?
Right.
Yeah. Is there something you can see from your...
So how would you see the E8 group?
I don't know. That's
so then I don't have to compare it to anything. That's good. So I can just say something. So these higher conserved currents, you would usually expect them at exponents of the group, and so for Ising you expect charges at sort of exponents of E8, and you can see that you can find charges at these exponents. So that's one relation to E8.
Sorry. So and those things are from they're a subset of your translation defect, is that right? Like this.
So if I do, so this is the magnetic field perturbation in the Ising model.
Yes.
And well, I'm saying alternatively, rather than looking at this perturbed defect, I could also search for such higher spin conserved currents which persist along the temperature perturbation, and their weights have something to do with the exponents of E8. But it's not directly related to this. There might be another relation, which is so the monoidal category you get out of these by looking at these Jetter-Drinfeld modules, that's related to representations of affine quantum groups, and so maybe that affine quantum group relevant here has something to do with C8, but that's something we didn't look at.
I see. Thanks.
All right, one last question.
Can we use this translation invariant defect to derive some selection rules on correlation function of local operators, similarly to topological defects?
Well, so how do you get the selection rules for topological operators, right? So you would have your correlator, and then you would try to drag your topological defect through the correlator, and then two things can happen. If it's a group-like defect, you get just some sort of group action on all of your local operator. If it's not invertible, then you translate your correlator of local fields into one which has disorder fields, right? Because you drag like little disorder lines out of your fields.
Let's maybe talk about the invertible case here.
And so these are typically, so the perturbed defects are typically not invertible, so that will not happen. So you can ask, can you get some sort of identity which is more like you change ordered correlator into a disordered correlator? That's also on the to-do list. It's sort of a little bit, not easily, because you can't deform these defects.
Yeah, but I can imagine to nucleate two of these defects and then passing, like parallelly, passing all the, if I like on the cylinder, I nucleate two of them, I pass all the others, and I re-annihilate it.
So that's certainly worth trying, but we haven't. So I can't say that gives an interesting answer.
Okay, thanks.
All right, let's thank the speaker again.